Welcome to Chapter 11, Nuclear Chemistry. Lots of interesting things to discuss here, and obviously there's been a lot of concern, especially recently, about exposure to radiation, and we'll hopefully show that some of that's beneficial, and some of it's really not too much cause for concern, and then again some of it is. So lots to talk about here in Chapter 11. Our learning objectives for this chapter are to identify the sources of natural radiation to which we're exposed, to list the sources and dangers of ionizing radiation, to be able to balance nuclear equations, identify the products formed by various decay processes. We should also be able to solve some simple half-life problems, use the concept of half-life to solve some simple radioisotopic dating problems, and write a nuclear equation for a transmutation and identify the product element formed. In addition, we'll be able to list some applications of radioisotopes, describe the nature of materials needed to block alpha, beta, and gamma radiation, explain where nuclear energy comes from, describe the difference between fission and fusion, and finally describe the goals of the Manhattan Project and how uranium and plutonium bombs were made. We'll identify the most hazardous fallout isotopes and explain why those are particularly dangerous. We'll list some uses and consequences of nuclear energy. And then finally we'll stick with our theme and explain how applications of green chemistry principles can be applied to handling of radioactive isotopes in spent fuel rods. Alright, so lots to talk about. Let's get right to it, starting with background radiation. Background radiation accounts for about 3/4 of all exposure for most of us to radiation. And then that remaining quarter comes mainly from medical irradiation, such as X-rays or nuclear medicine, if you've ever had tests that involve you being dosed with a certain radioactive isotope for medical tests. Okay, so if there's naturally occurring background, and that's the majority that we're experiencing, and then we also use it in medicine, how bad can this radioactive material be? Well, of course, there's the chance of radiation damage to cells in any of these events. Nuclear radiation is capable of removing electrons from molecules to form ions in the cell, and that's the term ionizing radiation. And that's one of the ways that a Geiger-Muller counter would detect radioactive isotopes being present, is by those ionizing radiation events. Finally, another way that damage to cells can occur is if the molecules are splintered into smaller neutral fragments called free radicals. So they're lacking a second electron, they have an unpaired electron, and these free radicals, when they're tearing apart cell material to find another electron, they can disrupt cellular processes as part of that damage. So you've often heard about free radical damage or ionizing radiation damage. Those are two of the main ways that radiation damage to cells occurs, and obviously neither one is desirable, but typically they're pretty small scale, and if we're talking about long-term exposures, then we have to worry about cancers and other risks. But in short-term medical uses like medical x-rays or medical isotope tests, there's very little chance of severe damage. So we worry about cancer as a consequence of exposure to radiation. Cancers are also often treated by radiation because radiation will affect the fastest growing cells and tissues more so than other cells. So in particular, white blood cells and bone marrow tend to be targets, as well as cancer cells. Cancer cells are rapidly dividing, and radiation therapy is part of the cancer treatment plan for many different types of cancer. So although the radiation exposures can cause cancer, they can also be used to cure cancers. And the main way that either of those events happen is due to our second bullet there on the slide. Ionizing radiation can disrupt DNA. So that can cause mutations that ultimately result in the generation of cancers. It can also disrupt the DNA of those cancer cells, the rapidly dividing cancer cells, and render them no longer viable, and therefore kill the cancer cells selectively, since the radiation damage tends to affect faster dividing cells more so than slower dividing cells. So sort of a double-edged sword here. The radiation damage can cause cancer, but radiation therapy can also be used to cure cancers. And if we take a look at the typical radiation damage to cell exposure routes, if we look, most of it is natural. About 82% of these radioactive damage events are caused by naturally occurring radiation. The majority of that being radon, a noble gas, a very heavy noble gas that's unstable and radioactively decays. And because it's a gas, oftentimes it can target lung tissue, which is very thin and very susceptible to radon decay, and the alpha decay there affecting that live lung tissue can result in lung cancers if you're exposed long-term to radon. And that's one of the reasons why they often will do radon testing of homes, and in particular the lowest level of the home where the radon is likely to concentrate. There may be vents installed if the radon levels are significant, or other precautions taken. We've also got cosmic rays from outer space. That's a much smaller amount. Internal, just radioactive isotopes inside our body. Rocks and soil. This is a lot of that naturally occurring background from uranium-containing minerals, for instance. Medical X-rays forms about 10%, a little over there at 11%. In nuclear medicine, another 4%, for about 15% damage from medical sources, and then much smaller amounts for consumer products and occupational exposures, etc. So most of us, all of us really, are exposed to some amount of radiation damage, but fortunately for most of us it's quite small, and it's not significant to damage large numbers of cells or cause significant risk for cancers. Speaking of radiation damage, we also have the electromagnetic fields generated by cell phone use. And so we see here when the cell phone is on, we see much greater activity there. And when the cell phone is off, we see far less of the red high-end radiation. So there's electromagnetic radiation from all the devices we know and love, and although I've seen some studies that indicate non-cancerous tumor increase in heavy cell phone users, I don't know that I've ever seen a link with actual causes of cancer. So it's one of those things that you have to decide whether it's worth it to have your phone up against your head for extended periods, or whether there's a time and a place for that. Alright, so by now, hopefully we're all experts in writing chemical equations. Here for nuclear equations, things get a little different. Chemical equations, we're used to the electrons doing the movement, and that's what we've been following for a long, long time now in the course. For nuclear equations, we're looking at those nucleons. For us, the protons and the neutrons, right? There's much smaller subatomic particles that physicists will go into, and even nuclear chemists. But here for our course, we focus just on the protons and the neutrons, and they've mainly been behaving themselves, doing nothing in the course of a chemical reaction. But here in a nuclear reaction, they're the ones that we tend to focus on. So looking at the atomic number, which is the number of protons for each of the species involved, and the mass number, which is the total sum of protons and neutrons, the number of nucleons, must be conserved during the reaction. So we don't lose protons, we don't lose nucleons, although we may convert them. So that's something to watch as we look through some of these nuclear equations. Alright, so if we're looking at our first example of nuclear decay, we look first here at alpha decay. And so alpha decay involves the loss of a small alpha particle, which is really the nucleus of a helium atom. It's 2 neutrons and 2 protons, and so that should look like a helium-4 nucleus, right? That's how we'll often denote it. And so as that large radon nucleus loses the small helium nucleus from itself, we transform here into polonium-218. So we've gone from radon-222 down to polonium-218 and helium-4. So sum together, we get a total of 222 for total nucleon count on left and right side, and we get a total 86 for the element radon, 86 protons. We get 84 protons in polonium, and then 2 more protons in helium to give a total of 86. So we still have the same number of nucleons and the same number of protons specifically, and that's a balanced nuclear equation, just like we're used to balancing electrons in a chemical equation. Our second example of a nuclear equation is beta decay. And the equation for beta decay here, we see a tritium, one of the isotopes of hydrogen, a tritium nucleus becoming a helium nucleus by emitting a beta particle. So a beta particle is a high-speed electron, and electrons we're familiar with, but this is an electron that's coming from the nucleus. So as you see, our hydrogen has 1 proton and 2 neutrons in the tritium isotope. And then our helium has 2 protons and 1 neutron for a helium-3 nucleus. So the way that we generate that beta particle, that high-speed electron that's emitted from the nucleus, is by converting a neutron, which is a neutral particle, into a proton and ejecting an electron. So if we think about a neutron as a proton and electron combined, now we can expel the electron part and leave behind the positively charged proton part. We already learned earlier in the course that protons and neutrons have roughly the same mass, electrons have almost no mass, so as long as we can simplify things and just consider a neutron to be a proton and electron combined, then ejecting that electron nature of it allows for an explanation of this beta decay process. Notice we still have 3 total nucleons, left side and right side. We have a total of 1 proton for the tritium on the left-hand side, and 2 for the number of protons in helium, plus the -1 for the electron, the beta particle, gives us a total of 1 for that side as well. So we've got the same number of nucleons and the same number of protons if we look carefully. Alright, so table 11.1 shows us those different types of radiations, the alpha particle that we've already talked about, and the beta particle we just finished. The gamma is actually light. It's electromagnetic radiation, very, very high energy light, not visible light, but much, much smaller even than X-rays, and therefore very, very high energy. Alphas are those big helium nuclei. They have a lot of mass. They have a charge of 2+, just like you would expect a helium nucleus with 2 protons to exhibit. And they're positively charged, so they are ionizing, but they are not good penetrators because they're such massive particles. They're not moving very fast, and they're relatively easy to stop. Beta, on the other hand, are much lighter particles. They're electrons, so they have a -1 charge, and they're moving quite a bit faster than the alpha particles, and so they have moderate penetrating power. And then finally, the gamma radiation, really it's like a very, very high energy photon of light that's emitted from a radioactive decay process, and this has extremely high penetrating power. This is what you need those thick lead shields to protect against. Okay, looking at another nuclear equation, we just talked about beta decay. Let's talk now about positron emission. So positron is sort of an anti-electron. It's a very light particle, but instead of being negatively charged, it's positively charged. And so it's similar when we just talked about a neutron being sort of a proton and electron combined, and the electron component is spit out and the neutrons left behind in the case of beta decay. In the case of positron emission, that proton can be thought of as sort of a neutron plus a positive charge component. So here we're just losing that anti-electron, that positron, and therefore if we look from left to right, we have our fluorine 18 decaying into oxygen 18 and a positron, Well, notice we have 18 total nucleons, neutrons plus protons. On the left, we have 9 protons in fluorine and only 8 protons in oxygen, and that's because the positron was a proton that was converted into a neutron. So the positron component was that positive charge of the proton, and instead now it left behind a neutron to have a total of 18, only now we have 10 neutrons and 8 protons on our oxygen 18, whereas we had 9 protons and 9 neutrons in the fluorine 18. So that's an example of positron emission, and we can also think about positron emission tomography if you want to think about the medical setting, and that makes great use of positrons for imaging. Okay, so our next example of a nuclear equation involves the first particle that actually comes from outside the nucleus. And this is called electron capture, where a nucleus absorbs an electron from the inner shell, so a very low energy electron that's close to the nucleus anyway, spends some of its time at the nucleus, and for whatever reason, that electron is captured in the nucleus. And so we have two reactants. We have the nuclear member, the nucleon itself here, an iodine 125 nucleus in this example, plus the electron, yielding a single product here, tellurium 125. So what we see, we take our iodine, which is element number 53 protons, and one of those protons pairs with this electron that is captured from the inner shell, and now that proton becomes a neutron. So we decrease by 1 in number of protons, and we increase by 1 in number of neutrons to give the overall nucleon number staying the same. So iodine 125 has 53 protons and 72 neutrons, whereas tellurium 125 has 52 protons and 73 neutrons. So we're just increasing the neutron count by 1 and also decreasing the proton count by 1 by having that proton and electron pair to become a neutron. So it's sort of the opposite process of beta decay, where the neutron spits out a beta particle, an electron, to give another proton. Here the proton captures an electron to give another neutron. Okay, and here we have table 11.2. Now we've added the positron emission and electron capture notation. So positrons are typically beta plus, and electron capture is an E minus absorbed. And we have their particle charge, no change in the overall number of nucleons, but in positron emission, you have a proton becoming a neutron, and in electron capture you also have a proton becoming a neutron, so the same net result there. For gamma radiation, we didn't show an equation, but typically we'd have just the letter M to denote that it's a metastable nucleus, and then on the product side we'd have no M anymore. So gamma radiation is actually the easiest to pick out because it doesn't change the proton or neutron count at all. It just goes from being a metastable nucleus to a regular old stable nucleus. And table 11.3 highlights some of the key differences between the chemical reactions we know and love and these new nuclear reactions we've been discussing. So in chemical reactions, again, it tends to be the electrons outside the nucleus involved in the reaction, so the atoms retain their identity in terms of the nucleons, the proton and neutron count. Whereas in nuclear reactions, obviously those tend to change from reaction to reaction. For chemical reactions, you usually only involve the valence electrons, whereas now in nuclear reactions we tend to involve mainly the protons and the neutrons, although as we see, some of those core electrons can be affected in something like electron capture. The reaction rates tend to increase with temperature for chemical reactions. That's why oftentimes we will put things in the refrigerator if we want to slow the decay processes and bacterial action on foods, for instance. We'll put them in the fridge to slow it down. For nuclear reactions, they tend to be unaffected by temperature. So when we had that disaster in Japan where the nuclear plant had a meltdown as a result of the tsunami affecting things. Fortunately, the increased rate of nuclear decay the temperature increase associated with that didn't cause anything to happen any faster. So that's a strange feature of nuclear reactions. They tend to be independent of temperature. For chemical reactions, they tend to be absorbed, or the energy given off or absorbed is fairly small compared to the huge energy possible in nuclear reactions. And then finally, in a chemical reaction, mass is conserved, right? We always talked about the law of conservation of mass. So the products and the reactants have equal masses. For a nuclear reaction, the way we get those huge energies given off is by converting some mass into energy. And this is where we get into Einstein's mass-energy relationship, E equals mc squared. Energy equals mass times the speed of light squared. Because the speed of light is a large number, 2.998 times 10 to the 8th meters per second for light in a vacuum, that's going to give huge energy changes even with small mass changes. So very, very small mass changes and binding energy that we'll talk about for the nuclei result in large energy given off in these nuclear reactions. Okay, here we see in table 11.4 just some of the symbolisms. So the symbol for proton, neutron, etc., and then the nuclear symbol, which oftentimes doesn't differ by much. It just will include the mass number and proton number, or charge number, to be more generic. A phrase that you've likely heard quite a bit whenever nuclear reactions are discussed is the phrase half-life. So the half-life of radioactive sample is the time required for 1/2 of the material to undergo radioactive decay. The longer the half-life, the fewer nuclei that are decaying in any given amount of time. The shorter the half-life, the more nuclear decay that's going on per given unit time. So we see here a graph for the radioactive decay of iodine-131. And if we start with the assumption that there's 16 milligrams total in the sample, well, after 8 days, we've elapsed 1 half-life. We've gone down to 8 milligrams remaining. And then another 8 days, we're down to 4. And another 8 days, we're down to 2. And it keeps going on until essentially none of the radioactive isotope remains. So obviously, when you have a short half-life like iodine-131, you don't have to go very long until essentially all of that radioactive isotope has decayed. If you have a long-lived half-life, like some of the things you'll find in geologic specimens, then we can be talking millions or even billions of years for decay. So if you want to know how much of the original sample remains after some number of half-lives, well, the fraction of radioactive isotope remaining is 1/2 to the n, where n is the number of half-lives. So if you want to know how much remains after 1 half-life, 1/2 to the 1 is 1/2, 1/2. If you want to know about 2 half-lives, 1/2 to the 2, 2 squared would be 4, so 1/4 would remain. 3 half-lives, you'd have 1/8, 4 half-lives, 1/16, and so on and so forth for whatever number of half-lives have elapsed. So if we look at table 11.5, we see a number of different isotopes with their half-life listed. And again, these half-lives are all in years. So some are in billions of years, like potassium-40 and uranium-238. Others, like lead-210, just 22 years for its half-life. Tritium, the hydrogen with a total of 3 nucleons, 2 neutrons and a proton rather, has a half-life of 12.26 years. And then finally carbon-14, the first one in the table, has a half-life of 5730 years, and it's very, very useful in dating things from about 100 to 50,000 years old. And that's a lot of organic material that really encompasses human activity here on Earth. And that's why we hear so much about carbon-14. All right, so following up on our love affair with carbon-14, we have carbon dating. The half-life of carbon-14, as we just said, is 5730 years. The carbon-14 that we take in while we're alive is formed in the upper atmosphere when ordinary nitrogen atoms are bombarded by neutrons from these cosmic rays we mentioned earlier in this chapter. And so that's a fairly constant process, and as long as the sample's alive, there's going to be that carbon-14 coming in. Once the sample dies, this is why it's useful for organic carbon-based life forms. Once you're no longer living and taking in new carbon-14, then that carbon-14 that's present will decay, and based on how much of that carbon-14 has decayed versus how much is still remaining, you can figure out how many half-lives have elapsed and get a pretty good idea of the age of the sample, again, to the nearest 100 years or so. So if you remember from that table, tritium had a much shorter half-life. Its half-life is only about 12.26 years, and so it's really nice for dating more recent objects up to about 100 years old. So whereas the carbon dating doesn't give us much detail in terms of fairly recent activity, again, carbon dating is more useful for that 100 years plus, way up to 50,000 years. Tritium, that form of hydrogen with 2 neutrons and 1 proton in the nucleus, is very useful for items up to about 100 years old. So the processes we've looked at so far are all natural, and transmutation is just the term for changing from one form to another. So like when we had the uranium undergo alpha decay in an earlier example, that was a transmutation. It changed its type because it was no longer uranium once it lost that alpha particle. The bombardment of stable nuclei with alpha particles or neutrons or other subatomic particles can be used to make new elements. This is how most of these transuranium elements have been made. And that process, because it's human activity causing it, it's humans bombarding these heavy elements with other particles, that's known as artificial transmutation. And it's pretty much how we've gotten every element beyond uranium to exist in the laboratory, especially these most recent elements that have just gotten their official names here, elements 118, and so a very, very recently made elements. So artificial transmutation is that process by which we create them. Radioactive isotopes are very useful as tracers. Tracers mean labeled isotopes that can follow processes through. This is how Melvin Kelvin won the Nobel Prize back for his work on the dark cycle of photosynthesis by following it with radioisotopes. Nowadays, tracers are used for lots of different things, including to detect leaks in underground pipes, to determine frictional wear in piston rings, to look at the uptake of phosphorus and its distribution in plants. Just really very useful because of their characteristics. These radioactive tracers are useful in a lot of different processes. So radioactivity can be a dangerous thing, but it can also be very, very helpful to human endeavors. Another example of radiation being a positive thing is radiation therapy. Nuclear radiation can be used to kill cancerous cells, again, because of that feature that we talked about earlier, where the radiation is most damaging to the fastest growing cells. Those cancer cells tend to be rapidly dividing, which is one of the reasons cancer is such a dangerous disorder. Well, we can make use of that to select out those rapidly dividing cancer cells with radiation therapy. The problem is the patients will typically experience some side effects like nausea and vomiting, hair loss, other things that we associate with radiation therapy because these are early signs of radiation sickness. The radiation is killing the cancer cells, but it's also killing other fast dividing cells like those in the blood, the red blood, white blood cells in particular, we said, the epithelial cells, the skin cells, the cells that line the digestive system. This is why we tend to see the nausea and vomiting effects. So again, it's not a desirable thing. There's a number of side effects, but when we're talking about cancer patients who are looking for relief and ultimately a cure from the disease, it's certainly worth the unpleasantness of these radiation sickness effects in order to get the cancer cells destroyed. In addition to using radioactive isotopes or radiation for cancer therapy, radiation can also be used as a diagnosis tool. So diagnostic uses of radiation are listed here in table 11.4, and you see there's a lot of different things. In particular, if you look toward the middle, we have iodine-131 that we looked at because of its short half-life of about 8 days. It's commonly used in thyroid diagnoses and therapy. So the thyroid selectively takes up that iodine. We've also got various types of cancer. We have lung tumors screened for with gallium-67. We have pancreas scans with selenium-75. Radium being used as radiation therapy for cancer. So lots and lots of positive applications of radioactive materials. And again, going back to Marie Curie, who discovered a number of these radioactive elements, understood that these could be useful in medicine. Probably didn't realize the level of risk involved at that time, but as long as we take risk into account and we do a cost-benefit analysis, there's still a lot to be gained from the use of radiation and nuclear isotopes in medicine. Right at the beginning of the lecture, we talked about the different types of radiation and the fact that background radiation is ubiquitous. It's everywhere. We can't control it. One of the reasons we shouldn't be too concerned about it is because a lot of that background radiation involves alpha radiation. Alpha radiation is the least penetrating, can't even penetrate our outer layer of skin, and it's stopped by a sheet of paper. And so that makes alpha pretty safe sounding. The problem arises with radon, which we talked about as well earlier in this lecture. Radon, because it's a gas, can be breathed in, and there, the outermost layer of lung tissue, those cells are susceptible, and alpha radiation can be very damaging because it's so massive if it gets into the lungs and into that fresh tissue, whereas our skin is mostly dead cells for several layers. The lungs are exposed cells, and that's the one time we do have to be very concerned about alpha decay. Beta radiation can typically penetrate a few centimeters of skin and tissue. It's stopped by a sheet of aluminum foil, so a little more than a typical piece of paper, but still not very good penetrating power. When we think about penetrating power, we tend to think gamma radiation, because that passes right through the body. You've got several centimeters of a dense element like lead in order to stop that gamma. So gamma tends to be the most concerning because of its penetrating power, but in terms of biological damage, alpha can be the most damaging if it gets in there into the lungs with those fresh cells. And here we just see an image where we have those massive alpha particles being stopped by that thin sheet of paper, the small beta particles being able to pass through the paper but being stopped by the aluminum foil, and then finally the gamma rays headed straight through that paper, straight through that foil, and ultimately needing several centimeters of lead to stop them. This is a lot more energetic even than the X-rays that you might have had, where they give you the lead vest to protect you a little bit. And X-rays, again, compared to gamma, are very low energy, so much thinner lead vest to stop the X-rays than you would need to stop gamma rays. Alright, so if nuclear radiation is a fact of life and it has its benefits, its uses, we have to consider how we protect ourselves from this radiation if we're going to be needing to be exposed to it at certain times. And the two means of protection are distance and shielding. So fortunately, the radioactive decay and radiation tend to be most concentrated right by the sample that's emitting them. So if you can move away from that radioactive source, the intensity of radiation decreases greatly with that distance increase. This is why if you work as an X-ray technologist or you work in the nuclear medicine facility, you tend to try to limit your time near the X-ray machine when it's actively working, right? You walk behind a shielded place while you take the picture of the patient. or you limit your exposure to the actual radioisotopes that you're going to be dosing your patients with wherever possible. The other option is shielding. As we already talked about, lead is commonly used as a shield, and that will allow other areas that don't need to be imaged, for instance by X-ray, to be shielded and not subject to the damage. All right, here's our good friend Albert Einstein. We already mentioned his famous equation. This was around 1905 that Einstein had developed an understanding of these relationships and exposed his famous mass-energy equation, E equals mc squared. And so energy is the result of a small amount of mass being converted into energy, and that mass-energy conversion is large because the speed of light, 3.0 or 2.998 times 10 to the 8th meters per second in a vacuum is a big number, and when you square that big number, even a small mass gives lots and lots of energy. So if we look at how this comes into play and where the energy from nuclear reactions arises, you have to think about the nucleus itself. So we've talked about nucleons as being the protons and neutrons. If we add these free nucleons, the mass of the free nucleons, just proton, proton, neutron, neutron, should be about 4.0320 atomic mass units. However, in the nucleus, in the helium-4 nucleus that has the 2 protons and 2 neutrons we just talked about, the actual nucleus mass is only about 4.0015 atomic mass units. So we've lost about 0.0305 atomic mass units. That's it's less than 1% of the mass, but it's a huge amount of energy when we consider that mass-energy conversion from Einstein's E equals mc squared equation. We call that the binding energy. That's the energy that goes into keeping those protons in particular, which are like-charged and want to repel. In order to keep them in such a small space, so close together, we need a lot of energy to do that, and that's where that energy goes as binding energy, to bind that nucleus together. So we see here a graph that shows us the binding energy per nucleon for the typical atoms that we encounter, just increasing nucleon number. We see iron 56 happens to be the most stable isotope. It has the highest binding energy, and that's one of the reasons that yellow dwarf stars like our sun can only create elements up to iron 56 because they're so stable. Our sun tends to stop there. The elements that we have above iron here on Earth probably came from the supernova of more massive stars. If you look, the binding energy goes down after that, which means things like uranium, as we look toward the end of the graph, have relatively less stable nuclei, and we can break those nuclei apart in things like nuclear reactors or nuclear weapons. So we tend to look at fission beyond iron because we're having large nuclei that have relatively lower stability and therefore can be coerced into breaking apart. If we look at the really small atoms like hydrogen and helium, we have fusion as our likely option, right? There's a relatively small binding energy per nucleon for things like deuterium, hydrogen-2, so we should be able to fuse those together. Fusion takes a lot higher temperatures and a lot more energy than fission to accomplish. That's why we don't have working fusion reactors here on Earth, just experimental scale setups, but obviously our sun is a great example of fusion in action, hydrogen fuel fusing together to make helium, and lots and lots of energy that we're very thankful for here on Earth. Alright, so looking at the Manhattan Project, the building of the atomic bomb, we first have to understand a little bit about nuclear fission. So fission occurs when larger nuclei split into smaller nuclei, and if we think back to that previous slide with that graph of nuclear binding energy, uranium doesn't have a huge binding energy. It has relatively lower binding energy, so it shouldn't take too much to split a uranium nucleus apart. we see even a slow neutron, what's known as a thermal neutron, can split apart a uranium-235 nucleus. This is why uranium-235 is the desired form, because it is what we call fissile. It can be split apart and undergo fission by even a slow neutron. And as you see, the results of that are 3 more neutrons as well as the daughters. Ultimately, first you get an unstable uranium-236 nucleus, which then decays into those 3 neutrons and the strontium-90 and xenon-143 isotopes. You also get some gamma rays, which are, as we said, very energetic and very good penetrators. So because the uranium-235 can undergo fission with a thermal neutron, and because each uranium-235 that we cause to undergo fission releases 3 more neutrons, we can have what's known as a chain reaction. We have a lot of that uranium-235 around. Well, every uranium-235 nucleus that decays is going to provide enough neutrons for 3 more uranium-235 nuclei to decay, and we can very, very quickly coerce a lot of uranium-235 nuclei into radioactive decay in a chain reaction. It's unstoppable. Once it gets to a certain critical mass, you would have just a very rapid, very energetic decay process. So we get one nucleus undergoing fission that causes other nuclei nearby to undergo fission, and that is a chain reaction. In a nuclear power plant, we have ways to slow that. We have control rods made of boron 10 actually, that can absorb a neutron to become boron 11 and slow the whole process down by removing some of those neutrons that are causing the fission in the first place. However, sometimes that chain reaction is exactly what you're after, and uncontrolled fission is the whole goal. And this was the goal of the Manhattan Project. So the Manhattan Project was launched by President Roosevelt back in 1939. It was a way to end World War II very quickly by demonstrating the power of the Allies when we were able to harness the power of the nucleus and the nuclear bombs. And there were 4 separate teams attempting to complete these goals. First of all, to sustain nuclear fission, to enrich uranium. Most uranium is 238, not 235, and so U-238 does not undergo fission with thermal neutrons, and so therefore it wouldn't be desirable. So we've got to find a way to make that small amount of U-235 that's present in nature able to be enriched to the level that it would be usable for a nuclear weapon. Another goal was to make fissionable plutonium-239, and then finally to construct a fission atomic bomb. And this is what the team came up with. They were able to develop the first atomic bomb, and of course we had our famous testings here in the States, mostly in the western state desert areas. The basics are a high explosive, just a chemical explosive that will cause this hollow uranium bullet to move rapidly toward its target, which is another uranium spike. And the reason for the 2 separate pieces of uranium are so that you have a subcritical amount, so that because once they're combined, you get a supercritical amount of uranium. That's an uncontrolled reaction. You can't stop the chain reaction once you have that much uranium together. So in order to prevent the bomb from going off before it reaches its target, you have to have those 2 subcritical amounts of uranium-235 separate. So once the bomb is dropped and the high explosive causes the rapid movement of the bullet toward its target, then you get the supercritical mass of uranium-235, and you get the classic mushroom cloud. And here we see that mushroom cloud over Nagasaki from the detonation of Fat Man on August 9th, 1945. Just tremendous devastation. Unfortunately, a lot of civilian life lost along with military lives, and another bomb was dropped later at Hiroshima, and by exercising that show of force, the Allies were able to end the war more quickly, but a number of the people involved, in particular Einstein himself, regretted their involvement in the project and the lives lost as a result. And one of the reasons these scientists exhibited the regret is because, in addition to the number of lives very, very quickly extinguished as a result of the immediacy of the bomb, you also have long-term effects from the radioactive isotopes. Lots of these isotopes that are generated in the nuclear bomb blast are especially harmful to human beings, and a couple of interests to us as chemistry students are strontium-90 and iodine-131. Strontium-90, with a half-life of 28.5 years, is chemically very similar to calcium, right? Strontium's the next element in group 2 under calcium. So it's going to behave a lot like calcium, and therefore when it's ingested in contaminated dairy from cows that have been eating grass that are contaminated with these radioactive fallout isotopes, it ends up in human bone or other animal bone, and can cause bone marrow cancers and painful consequences and ultimately death to humans who've been exposed. And again, with that long half-life, it can be for generations. Iodine-131 has a much shorter half-life, but it has the same problems. It concentrates in the thyroid gland. If you have too much of this radioisotope, it can damage the thyroid, can cause a lot of bad effects to human metabolism and human health. Okay, so let's focus, instead of the military application of the atomic bomb, let's look at the civilian nuclear power plants. Here you're using uranium-235 that is far less enriched, so about 2.5 to 3.5% U-235, rather than the 90% that's used for nuclear weapons. So it's a lot easier to enrich to that smaller level. It's also a lot safer, and even countries that have had a history of issues, to say the least, like Iran, are permitted to have now enriched uranium for nuclear power plant use because it's such a small amount. Certainly it does open up the problem of perhaps further enriching and getting nuclear weapons, but that seems like something that's a small enough risk that the world community is willing to take it, at least for the moment. The nuclear chain reaction here in a power plant is controlled so that you get a slow release of heat energy. As I mentioned earlier, you have these control rods that can absorb those neutrons and limit the amount of U-235 that can undergo fission. And for the most powerful force in the universe, this nuclear force, the way that we use it to heat water to make steam, and then the steam turns a turbine to produce electricity. So sort of a letdown, I think, for the greatest force in the universe being used to boil water. But that's how we do it, and that's how we produce electricity, and that's how people who live very close to nuclear power plants, like the power plants up in Oswego or down in Pennsylvania at the 3 Mile Island facility, for instance, the residents enjoy a very low electric cost by having this very close, very cheap, and reliable source of electricity. Okay, so nuclear fusion is a thermonuclear reaction in which smaller atomic nuclei are fused into larger nuclei. And as I mentioned earlier, fusion is the principal reaction in the sun, where you have those hydrogen isotopes fusing into helium and generating lots and lots of energy. This is much more desirable. The waste products are helium, which is not an especially dangerous product. So ultimately, we would love to be doing fusion here on Earth rather than fission, which does have some long-lived isotopes that can be problematic for long-term storage after they've been produced in fission power plants. But fusion so far has eluded us. It's just difficult to get the conditions here on Earth that would allow for fusion, controlled fusion, to take place and to actually generate more energy than it costs to get the heat and the magnetic field and all the different conditions correct. So hopefully in the future fusion will be the way to go, but for now nuclear fission is our energy producer. Okay, and so finally we end with an example of all the benefits of the nuclear age. Um, nuclear fusion, or fission rather, controlled nuclear power generation has a lot of potential drawbacks. We have had some incidences. 3 Mile Island, for instance, in Pennsylvania, they had an uncontrolled release of some radioactive gases a number of years back. Um, didn't seem to be terrible. Again, it did cause some concern in the short term, but doesn't seem to cause long-term issues, whereas Chernobyl, the reactor in the former USSR, still has a dead zone as a result of its meltdown. And then the Nagasaki plant, which was caused by natural disaster, the tsunami and earthquake, has now made that area quite a dangerous place to be in terms of background radiation. But aside from those relatively few, mainly human incidences, Chernobyl and 3 Mile Island were the result of human errors, humans overriding safety issues that they shouldn't have. Nagasaki being natural, we can't fault the Japanese for the tsunami and the earthquake. But ultimately, despite its potential drawbacks, nuclear energy has been a pretty reliable and safe source. It doesn't have the carbon emissions that we're often concerned with these days in terms of what that carbon dioxide is doing that's being released by burning fossil fuels. So fairly strange to say it, but nuclear energy is often labeled as green energy now because it does not have the carbon emissions that we associate with burning of fossil fuels. And we see all of these benefits that we can achieve now because of our understanding of nuclear processes and radioactive decay. So hopefully you've enjoyed this chapter as much as I have, because there's a lot to really be quite in awe of when it comes to nuclear chemistry.